Okay, in this session, we are going to discuss some problems on simple stresses and strains. So, means the topics what we have covered in previous 8 sessions. So, right, that is definition of stress, types of stresses, and types of strains, and stress strain diagram, and different formulas involved in the topics. And also, we have studied the stress strain diagram and respective formulas like so Hooke's law, how the strain and stress are proportional to each other, and there is some elastic constants. There are three types of elastic constants and how they are related to each other, and Poisson's ratio, how the Poisson's ratio is involved in calculating the elastic constants. These are all we have studied in previous sessions. So now we'll solve some more problems based on the topics covered in previous sessions. So now this is a problem. A hollow steel column has to carry an axial load of 3 meganewton. So 3 meganewton means it is 10 to the power of 6 Newton, right? If the external diameter of the column is 300 mm, find the internal diameter. The ultimate stress for steel, is to be 480 Newton per mm square. Take factor of safety as 4, right? So first understand what is given in the problem. A hollow steel column has to carry an axial load of 3 meganewton. 3 meganewton, this is a load the steel column carries. If the external diameter of the column is 300 mm, this external diameter, it means the given the steel column is of hollows like this. So it is having the outer diameter, or I can say the external diameter this, and internal diameter is this. This is internal diameter. Now the external diameter, this is given in the problem, this is 300 mm. This is 300 mm is given in the problem, and he is asking this diameter, right? So meanwhile he has given the ultimate load or ultimate stress he has given. From the ultimate stress you need to calculate the safe stress or working stress or design stress. So all three are same. You need to calculate first that with the help of factor of safety. So the safe stress or working stress is given by ultimate stress by factor of safety. So this symbol I told you, we are using sigma throughout our discussion, but in this book he used a small f for stress representation. Representation may vary, but the concept remains same here. So the sigma by fs, substitute sigma value given in the problem, 480 divided by 4 is equal to 120 Newton per mm square, right? So this is what working stress or safe stress now. So now we know that the stress formula, that is a sigma is equal to P by A. So substitute sigma, that is safe stress, and load given in the problem, then find out area. Why you need to find out area? Because he is asking you to find out the internal diameter. Internal diameter comes in area. So right, so find out area. Area is equal to P divided by safe stress. P is 3 into 10 to the power of 6 divided by 120. So this is equal to 25,000 mm square. This is the area, right? So now we know that what is the formula to find out the area of a hollow column. So that is pi by 4 d1 square minus d2 square, where d1 is external diameter and d2 is internal diameter. External diameter is given in the problem, that is 300 mm, but he is asking d2 value, right? Substitute value of A, that is area, is 25,000 equal to pi by 4 d1 square minus d2 square, right? Substitute the value, given values in this formula. Pi by 4, 300 square is external diameter minus d2 square. So you need to find out d2 square. So keep this term here only. So bring this one this side. So 25,000 into 4 will come. This pi will come downside. So this is 300 square minus d2 square is equal to 25,000. So divided by pi into 4. So d2 is equal to square root of 300 square minus 31,830.99. So the value will be 241.2 mm. This is the internal diameter. So internal diameter must be less than the external diameter. So we got the answer as 241.2 mm. So the next problem is a short column has an internal diameter of 200 mm. So in the previous problem, he was given the external diameter and he asked the internal diameter. But in this problem, he has given the internal diameter. Now he is asking to find out external diameter. So both are same. Both are same. So in the previous problem, the internal diameter was unknown, but in this problem, external diameter was unknown. So the concept is same. So what should be the minimum external diameter so that it may carry a load 1600 kilonewton with factor of safety 7.5. Take ultimate stress of steel as 472 Newton per mm square. Again it is same. So find out D1, he is asking D1, this is internal diameter, D2 is given in the problem. So sorry, D1 is external diameter, so it is asking for external diameter, and D2 is internal diameter is given as 200 mm. So P is 1600 kilonewton. 16 kilonewton means it is 10 to power of 3 Newton. Kilo means 10 to power of 3. If you want, you can write it 10 to power of 3 Newton. Factor of safety is 7.5. Again, similar to the previous problem, first find out the working stress. Whenever the ultimate stress is given in the problem, then you need to find out the safe stress always when factor of safety is given. So now the safe stress is ultimate stress by factor of safety. So this is equal to, this is sigma divided by Fs, 472 by 7.5. So that is equal to 188.8 Newton per mm square. So this is the safe stress. With the help of this safe stress, then using the Hooke's law, again find out the area now. The safe stress, this is sigma is equal to P by A. So sigma is just now you have calculated, that is 188.8 Newton per mm square. So that is equal to 600 into 10 to power of 3 divided by A. So now A will go on this side. So 188.8 comes on the downside. So A is equal to 600 into 10 to power of 3 divided by 188.8 is equal to 8.47 into 10 to power of 3 mm square. So this is the area. Similarly, again you apply the formula for the area. So area is equal to pi by 4 d1 square minus d2 square. So that is 8.47 into 10 to power of 3 is equal to pi by 4 d1 square minus 200 square. Right? This is 200 square. So now if d1 square minus 200 square is equal to 8.47 to 10 to power of 3 into 4 divided by pi is equal to 10784.33. Right? So d1 is equal to this square root of 10784.33 plus 200 square. So d1 is 225.35 mm. This is the external diameter. Internal diameter was 200. External diameter is 225.35. So external diameter is more than the internal diameter. So now we'll see a steel bar 2.4 meter long and 30 mm square is elongated by a load 400 kilonewton. If Poisson's ratio is 0.25, find the increase in volume. Assume E is equal to 200 kilonewton per mm square. Right? Write the given data. So he has given L is equal to 2.4 meter. It means 2400 mm. 30 mm square he has given. Square means it should be like this. The square. Right? So this is also 30 and this is also 30. So you will get area is 30 into 30. 30 into 30 will give you the area. That means it is 900. 900 mm square is the area. 900 mm square is area. P is given as 400 kilonewton. It means 400 into, it is 400 into 10 to power of 3 it is. 10 to power of 3 Newton. This is the load. Then he has given the Poisson's ratio. 1 by m is 0.25. Poisson's ratio is also represented by mu. Mu is equal to 1 by m is equal to 0.25. So now E is calculated m now. With this 1 by m is 0.25. So m is equal to 4. So E is 200 kilonewton per mm square. So it means into 10 to power of 3 Newton per mm square. Right? So what he is asking is find the increase in the volume. So first find out the original volume. original volume V is equal to L into A. So that is equal to 2400 into 30 into 30. 30 into 30 is area. So this is length is 2400. So now the answer is 216 into 10 to the power of 4 mm cube. This is the volume is mm cube. So find out the longitudinal strain. Delta L by L is equal to P by AE. So delta L is PL by AE. Now you are calculating longitudinal strain. So delta L by L, P by AE. So that is equal to 400 into 10 to the power of 3 divided by, this is again 900, this is area, and E value is 200 into 10 to the power of 3. So now you will get 2.22 into 10 to the power of minus 3 is the longitudinal strain. Longitudinal strain means it is epsilon L, longitudinal strain now, right? So next is volumetric strain. Volumetric strain means delta V by V. So that is delta L by L. So that is 1 minus 2 by m. So that means it is epsilon. Substitute the value of delta L by L, that is epsilon L here. 2.22 into 10 to the power of minus 3. So 1 minus 2 by 4. Right? So now you can take m here as 4, or else you can directly substitute 2 mu. 2 mu value means 0.25. So in this problem, or I can say in this book, he found out m value and he substituted a m value, or else you can use epsilon L into 1 minus 2 mu. This is also correct. Substitute the value of mu directly here. It is given 0.25. So this answer will also come as same, right? So that is equal to 2.22 into 10 to the power of minus 3 into 0.5. So that is equal to 1.11 into 10 to the power of minus 3. So now find out change in volume. Delta V is equal to 1.11 into 10 to the power of minus 3 into V. Now this V comes on this side. So delta V will be remains on the left hand side. So 1.11 into 10 to the power of minus 3 into 216 into 10 to the power of 4. So now you will get it, the change in volume as 2397.6 mm cube. This is the change in the volume. So next problem is, the Young's modulus for a given material is 100 kilonewton per mm square. This is Young's modulus, and its modulus of rigidity is 40 kilonewton per mm square. Determine its bulk modulus and also its lateral contraction if the diameter is 50 mm and length 2 meter and extension is 2 mm. So write down the given data. What he is asking, determine its bulk modulus means he is asking K, and also its lateral contraction. Lateral contraction means epsilon D he is asking. He is asking epsilon D. Epsilon D, lateral contraction, lateral strain he is asking. And length is given 2 meter, diameter is 50 mm, and extension 2 meter. Extension 2 meter means delta L is given. So write down E is equal to 100 kilonewton per mm square. Kilonewton means 10 to the power of 3. C is given, that is modulus of rigidity is 40 kilonewton per mm square. 40 kilo means into 10 to the power of 3 again. D is equal to 50 mm. Length is 2 meter, convert it into mm because all units should be in the same units. So convert meter also to the mm. So it is 2000 mm. Delta L is 2 mm. So now we know that C is equal to m epsilon divided by 2 into m plus 1. So E is equal to 2C 1 plus 1m. It means, so you know this is 2C inside bracket 1 plus mu. This was the formula, right? So now find out 1 by m is E by 2C minus 1. Substituting all the values, you will get m value as 4, or m value as 4, or you can get it mu value also. Mu is 1 by m. So mu is 1 by m, that is equal to 0.25. It should be 0.25. It will come 0.25 because 1 divided by 4. You can take mu and write the formula in terms of, you can write this formula in terms of mu, take the value of 0.25, or if you write this formula in terms of m, then you can substitute the value in terms of m here, right? So now substituting the values, 4 into 100 into 10 to the power of 3 divided by 3, 4 minus 2. So that will works out to be 66.66 kilonewton per mm square. This is the bulk modulus. Then longitudinal strain epsilon is delta L by L. So delta L is given as 2. Then L is 2000. This is equal to 0.001. Lateral strain is delta D by D. So that is equal to 1 by M into epsilon. So 1 by M is 1 by 4. 1 by M is mu. So is 1 by 4 into 0.001. That is equal to 2.5 into 10 to the power of minus 4. This is the lateral strain. Change in diameter or lateral contraction delta D is given by delta D is how much? Delta D, you know already, this is epsilon D. Epsilon D is equal to delta D divided by D. This was the formula. So now you need to find out delta D. If delta D you want, then multiply D with this. So this is epsilon D into D. So that's what he has done here. The 2.25 into 10 to the power of minus 4 into D. So this D multiplied here. So right, 2.25 into 10 to the power of minus 4 into 50. So you will get the answer as 0.0125 mm. This is the change in the diameter or lateral contraction delta D. So right, so he was asked, this is the bulk modulus, this is the lateral strain, and this is the change in the lateral diameter, lateral direction dimension, that is delta D. So these two problems I given it for your practice, right? So this PPT I will give for you as a link. So these two problems you can practice at home. So I'll tell you, a bar of steel 1 meter long, 50 mm wide. A bar of 1 meter long, 50 mm wide, 10 mm thickness, right? So he is subjected to an axial load of 10 kilonewton in the direction of its length. Find the changes in the length, width, thickness and volume. So practice this. Then next problem, a bar of 30 mm diameter is subjected to an axial pull of 80 kilonewton. The measured extension is 0.1 mm on a gauge length of 200 mm and change in diameter is 0.004 mm. Calculate the Poisson's ratio and the values of Young's modulus, bulk modulus and modulus of rigidity. So these two problems are very important. So practice at home. So whatever he has given, write down from this, then try to write the formula. If you write the formula, then you will understand. So what is the unknown in that formula? Then that unknown you need to find out. So this all these problems I have taken it from the Strength of Material by P.G. Munda's book. So thank you.